Alright, AP Physics C, gonna go through the supplemental problem. I'll post a PDF of this ASAP. In fact, you know what? I'm gonna pause this immediately and do that before I resume the video. Okay, just got this solution updated. Now, this is kind of funny, but I had done this video. I did this awesome video, right? And I got all the way through it. And right in this one part, I'll tell you when I got to it, I made a mistake. And I kept going through it. And then I like literally did exactly what I told you not to do. I made the mistake. And I've done it before, distributing a negative sign. I got to the end and I was like, huh, that acceleration seems too big. And then sure enough, when I started checking it, I was like, gee, that's not working out. So it's kind of funny. I might post that video, but anyhow, let's get through this and take a look at it here. I'll try to be as quick as possible. The solutions are already posted, so take a look at it. So this is a problem you definitely need to know how to be able to do, where you have two boxes, two masses attached via a pulley, and the pulley's mass now cannot be ignored. Now, most of the time in real life, the pulley's mass is really not that important, but you still have to know how to factor it in. So each of these, I'm going to call this M1, M2, and capital M for the pulley. Pulley has a radius R. Alright, those are all given to us in the problem. There's a coefficient of friction on the desk, that's given to us. And it asks us to first draw force diagrams for each object. So I guess I'll do those up here. I'm gonna go from left to right here. So mass 1. It asks for the point of application, which is a force diagram. So there's FT1. The point of application isn't so important for the two objects that are moving linearly, but it is important for the object that is rotating, because the point at which the force is applied determines the magnitude of the torque. Alright, so there's object 1, the pulley. Alright, the pulley does have a support, and sometimes you have to figure that out. In fact, the pulley you can draw two different force diagrams for. Well, really, you can draw a force diagram and a free body diagram. I'll draw the free body diagram for the pulley in a minute. Usually we draw free body diagrams for these types of things, but for rotating objects it matters. This is, I'm going to call FT2. I'm going to call this one here FT1. So these are both FT1. Action-reaction pairs is the force of the rope on mass 1, force of the rope on the pulley. FT2 should be bigger, actually, so I didn't do a good job drawing this to scale, but oh well. And then the hanging mass, right? FT2, FG, and, 2, FG pulley. Alright, so those are force diagrams. Free body diagrams are when we would draw them, represent the objects with a point, right? And really that's probably more useful than, for the linear moving objects than the rotational one. But you can draw a free body diagram for the pulley as well. Now, that angled force is the force of the desk. And what's kind of interesting is this must also satisfy Newton's second law, this diagram. Alright, so these forces, it must actually balance out as well. So the force of gravity on the pulley plus force of tension must equal the x component of the desk force, and force of tension 1 must equal the, y component. Force of tension 1 must equal the y component of the desk force. That also must be true, right? Because the whole pulley is not accelerating anywhere. So it's static when you look at it in a free body diagram, because it doesn't have any linear acceleration moving anywhere, but it's dynamic, meaning it's accelerating when you look at it from a point of application because it's rotating, right? So it's two ways to draw it, and I'm just going to skip it. Well, I'll just do it really quick. FT2 and FG2. All right, so free body diagrams, force diagrams. It's almost like this one, the free body diagram for number 1, the force diagram for pulley 2, and the free body diagram for number 3 is kind of what you want to do. I asked you just to draw force diagrams at the point of application. Now, part B asks us to record Newton's second law equations for each object. All right, now, yes, you could make X and Y. You could, for the pulley, you could do torque and X and Y. We're only going to do the ones that we need. All right, so I only need the ones in which shows the acceleration. So for this one, right, I'm going to say this direction's the positive acceleration. For this one here, I'm going to say positive direction is the direction it's accelerating in rotationally. For this one here, I'm going to say down is the positive direction. And again, it's totally up to you to decide what to make direction positive, but my advice is to always make the direction of acceleration positive. So now I'm going to make the Newton's second law equation. So for mass 1, I'm going to write it over here on the side. The direction that matters is the x direction. And to the right is positive for this guy. So Ft1 minus force of friction, I'm going to go ahead and write mu m1g. I know that the force of friction is mu times Fn. I know that Fn has to equal m1g because it's not accelerating up or down. Equals m1a. Great. All right. Let me give it a little space there. Then I'm going to do the pulley, which is mass capital M and radius R. All right. All right, so the pulley, I'm doing net torque here. So Ft2 is our positive torque the way I've drawn it. So Ft2 times R plus, or I should say minus, Ft1R equals I alpha for the pulley. All right, we'll simplify that down in a second. All right, so, well, why don't we go ahead and do it now. Alpha always equals A over R, right? Whatever rate which that string is going over the surface of the pulley, pulling it, that's going to be in meters per second squared. If I want to figure out how many times it's going to rotate, or how fast the angular acceleration is, I have to multiply A times R. Or alpha must be equal to R times alpha. Alpha must be equal to A over R here. All right. Then I, since it's a solid disk, it's 1/2 mr squared. All right. Those you can look up anytime on a quiz or whatever. Okay. You're going to have those accessible for the AP exam. So go ahead and look them up. All right. So when I plug all this in, I get 1/2 mr squared times A over R. Again, those R's cancel. Boom, boom, boom. And I know some of you are having difficulty with this conceptually, this topic, but to be honest with you, it's really, the conceptual stuff is just setting up the force diagrams. It's mathematics after that. It's algebra. It's a lot of algebra. Sorry, but that's what it is. All right, so I can simplify this down now. Ft2 minus Ft1 equals m over 2 times A. All right. And my final third law equation is for M2. That is simply going to be M2G minus Ft2 equals M2A. And again, I said down was positive over here. So it's the force of gravity minus the force of tension equals MA. I want the A's to all be positive here. And now I have to do the algebra. All right. So again, I'm looking for the acceleration. All right. I'm gonna erase our force diagrams here. I will draw them again, probably at some point here, to do some figuring out later on. I have three equations that I'm using. Right. I've got. Let me get a different color marker for this. I'm gonna call this equation 1. I'm gonna call this equation 2, and this equation 3. It's a funny little marker, came with the whiteboard, but it's helpful to add a little color in there. So equation 1, I'm actually going to rearrange equation 1 a little bit. I'm going to solve it for the force of tension. 1, Ft1 equals m1a minus mu m1g. Equation 2 I'm going to leave alone, so this is my equation 1 now. Equation 3, I'm going to solve it for Ft2. So I'm going to have Ft2 equals m2g minus m2a. So now these are my new equations, all right? And I think I will rewrite these maybe over here, equation 1, 2, and 3, and then give myself some room for the algebra. So equation 1, we got Ft1 equals m1a minus mu m1g. Oops, made a sign error there. Whoops, plus. Man, almost did it. Move this over there, it becomes positive, obviously. You fool. And you know how I caught myself there? Because I thought conceptually for a second. I said, wait a minute, okay, so Ft1's got to be bigger than friction. All right, it's going to be bigger than friction by m1a. All right, so force of tension, if it was static and it wasn't accelerating, it would just be equal to m1 or mu m1g, the force of friction. But since it's accelerating, I need to add a little bit more force to the tension. The little bit more force you're adding is the required amount to accelerate it, m1a. So when I looked at it, I said, wait a minute, that's not right. Ft1's got to be bigger than, it's not m1a minus, it's got to be added on to friction. Bam, that's right now. All right, so then that's equation 1. Equation 2, I'm just going to leave it exactly as we wrote it. m over 2 times a. For equation 3, I have Ft2 equals m2g minus m2a. Yep, that's right. Ft2 comes over here. I'm just gonna, it's got to be, Ft2 has got to be smaller than the gravity, right? Because Ft2 is going up. Ft2 has got to be smaller than gravity because the net force needs to be down. So it's at gravity minus the net force, minus that extra bit. And there we go. I'm going to erase this over here. I'm going to leave the drawing of the setup for now in case I need to go back. But I've got equation 1, equation 2, and equation 3. Now, I'm going to go ahead and substitute some stuff in here and do some algebra. Well, the general practice here is to take 1 and 3 and plug into 2. So take 1 and 3 and plug into 2. So it's going to be Ft2, which is m2g minus m2a, minus Ft1, which is going to be, this is where I made my sign error. And I even did it exactly like this, which was frustrating, but anyhow. The sign error here would be if you do not properly distribute that negative sign, right? So actually, if we write this as m2g minus m2a minus m1a minus mu m1g equals m over 2 times a. All right? I'm just doing algebra at this point. So now we have to solve for a. So on the left side, we have m2g minus mu m1g. And this is where I should have noticed the mistake I made in the previous one, but I didn't. And then I'm going to bring these two over to here. So it becomes m over 2 plus, I'm just going to go ahead and group them right here, times a. You guys are seniors. You should know how to just, you know, remove that A, pull that A out to the side or in front, whatever you want to do. So it's the sum of all the masses, so to speak, times acceleration. If you think about the blob method, what external forces are acting in the system? Well, m2g and the force of friction, which is mu times m1g. So m2g is trying to pull it to the right, friction is resisting it, mu, friction's resisting it, and that has to be equal to the total mass, which you might remember is m over 2 plus m1 plus m2, and look, that's where you end up. So the blob method does work for this one as well, using that kind of approximation thing that I showed you with, you know, you treat the mass of the pulley as the coefficient from the moment of inertia times the mass. So anyhow, here we are. Acceleration of this system is m2g. I typically don't pull that g out in front there. I don't know why. Just typically don't. Over m over 2 plus m2 plus m1. Pulling the g is probably kind of nice to do. So it'd be m2 minus mu m1 over capital M over 2 plus m2 plus m1 times g. And you plug everything into that, and you get an acceleration of 3.1 meters per second squared. Well, that's cool. So this is accelerating down at 3.1 meters per second squared. This one's accelerating to the right at 3.1 meters per second squared. And the angular acceleration of the pulley would be its radius, which is 0.04 times 3.1 meters per second. So you could get the angular acceleration from that. I didn't ask you for that, but you know, it is what it is. So 3.1 meters per second squared. Good. Part C. Now, when I did it the first time, the first indication that it made an error was because it came out to be like 7 almost, or 6.5. And I said, wait a minute, that is a little bit too big. All right, it's a little too big. How do I know? Well, you know, I just had a feeling. So when I went back and checked it, sure enough, I made that sign error. But hopefully you got it now. All right, so once you have that acceleration, then you can go back for part D and use that in equation 3 and equation 1 to get the force of tension. Now, one thing that you ought to note, FT2 darn well better be bigger than FT1, because we know this needs to accelerate that way, right? So FT2 darn well be bigger than FT1, otherwise it's not going to accelerate, right? Now again, they're not the same tension, but you know. All right, so let's go ahead and do that. So in equation 1, FT1 must equal 0.5 times 3.1 plus 0.33 times 0.5 times 9.8. You get about, what do we get there? 3.2 newtons or so. And then FT2, plug everything in, you do 0.5 times 9.8 minus 0.5 times 3.1, and you get FT2 equal to about 3.4 newtons. Awesome. I forget what they really are. It's like if you do 3 sig figs, you get a little bit bigger, but we're only going to do 2 sig figs here, or 1 decimal place, I suppose. If you're doing proper sig figs, this would be 3.2 and 3.4. Now what you can do is you can go back and check it with the pulley, and I did this on the PDF solutions. You get, so when you plug in, you know, okay, go back to plug into equation 2, it's FT2, so it's 3.4 newtons minus 3.2 newtons. equals m over 2 times a, so it's 0.1 divided by 2 times 3.1. Well, on this side, because I've rounded it so much, you only get really technically 1 sig fig. And then on this side, when you do it, you get like 1.56 or something, or sorry, 0.156, but to 1 sig fig, guess what? That's 0.2. So it's a little bit of a hand wavy thing. If I had put more decimal places on here, you would see that it would work out very, very, very well. Anyhow, there's a supplemental problem. Sometimes you do get asked to figure out that force of the desk. So this is a bonus. Stop watching now even if you made it this far. But this is a bonus level question, this part here, okay? So the one question is, okay, what magnitude of force is the desk supplying to the pulley? Well, you really got to look at the free body diagram for that. So you have the weight of the pulley. I'm going to do this very quickly. So it's 100 grams. So 0.1 times 10 is 1 Newton is the weight. Right? You have the push of the desk supporting it. Force of the desk. You have FT. This is FG. This is FT2, which we said was 3.4 newtons. And then over here, we're going to have FT1, which is 3.2 newtons. So the desk here, all right, I kind of alluded to this. We can look at that desk vector. The x component has to be equal to 3.2 newtons. The y component for this desk, it must support both the weight and tension 2 pulling down on the pulley. So this has got to be a y component of 4.4 newtons, which is kind of cool. So then this has to be, the magnitude of the desk has to be equal to the square root of 4 squared plus 4.4 squared plus 3.2 squared. And you get, real quick, 4.4 squared plus 3.2 squared equals 5.4 force of the desk newtons. And yeah, you could get an angle here, theta. You guys can all do that. Tan inverse, second tan of opposite over adjacent, 4.4 divided by 3.2 is force of the desk. Theta ends up being like 54 degrees. So that's like a bonus thing sometimes asked in the AP Physics C exam, to figure out, go back to the free body diagram for the pulley and figure out how much force. Because sometimes they'll be mean and it'll be like something like this where it's not on a desk. It'll be like on a string, a pulley on a string. And there's a mass hanging from it and some random force pulling this way. So you got to figure out the force of tension in this string. Well, that depends, right? It's basically the same setup. Anyhow, went over time. Hopefully everybody's all right. I'm going to make a little video on how to use these videos. You know, watching them and just watching me do stuff doesn't help. You want to try to kind of take notes on them, right? That writing aspect of it. You want to take notes on them. All right, talk to you later.